record a short video here just to outline some information about a two-way analysis of variance. And this video is by no way comprehensive for this subject. This is really more a quick and dirty video for understanding when to use two-way ANOVAs and how to think about them really overall. So to start out with this, when we're talking about a two-way analysis of variance, essentially what we want to consider is a situation where there's more than one variable or factor that could potentially be impacting something that we're interested in measuring, some kind of phenomenon. So I usually like to use a pretty straightforward example for this of kind of thinking about combinations of ice cream flavors and toppings and how delicious they are, because it's pretty fun to think about ice cream. So there's multiple things that can make an ice cream experience more or less delicious, and one of those is potentially the flavor of the ice cream. So this is my first factor. And for the sake of this quick example, I'm just going to pick two flavors, and you'll see why in a little while. So the two flavors I'm going to look at are chocolate and apple pie. Okay? So, that's one factor that can influence, how delicious some ice cream might be. But along with that, the topping can also influence how it tastes. So my second factor here is going to be the topping, okay? Right, and the toppings are different from flavors, right? They're kind of a qualitatively different thing about the ice cream experience. And the two toppings that I'm going to choose for this are sprinkles, and then along with that, cheddar cheese. And this might be where you're going, what? But bear with me, you'll see what I mean by this. Okay, so now if I'm starting to think about, all right, doing some taste tests and evaluating, the deliciousness of my ice cream flavors, right? I could create a graph of that, right? So flavor on my x-axis. Right, and I've got chocolate and apple pie. Right, and then my y-axis would be deliciousness. Right, and I realize everyone's a little different in terms of their ice cream preferences, but let's just say that I prefer chocolate ice cream more than apple pie ice cream. Okay, so just in general, if you were to have me rank deliciousness, chocolate would be somewhere up high, apple pie would be somewhere down low. Okay, but now let's think about combinations of these ice cream flavors with the toppings. Okay, so I'll just note that when it gets down to it, if you put sprinkles on chocolate ice cream, I'm a fan of sprinkles, so that actually makes the chocolate ice cream even more delicious. So if I were to graph where sprinkles would be for me, sprinkles would be somewhere up here. And then in contrast, if I were to graph chocolate ice cream with cheddar cheese, well, I don't know about you, but to me that sounds like a really weird combination. So that's going to wind up being somewhere down here. Okay, so here's where cheddar cheese would be for me. All right, and now let's think about these with apple pie. Apple pie ice cream and sprinkles, that's okay, but to be honest, it's still not nearly as good as chocolate ice cream with sprinkles. So for me, apple pie with sprinkles is going to be somewhere down here. And then now if you think about apple pie and cheddar cheese, this is where things get interesting. So historically, actually, people used to add cheddar cheese, and some do today, because it turns out, for some reason, if you think about cheese and apples, they're actually a really great combination. So if you mix together apple pie ice cream with some cheddar cheese sprinkles, well, that winds up being somewhere around here. Like for me personally, it's still not quite as good as chocolate ice cream with sprinkles, but apple pie ice cream with cheddar cheese, fairly tasty combination. So here's the really important thing in all of this. If I were to ask you, well, what kind of ice cream is the most delicious in the context of what I've illustrated here, right? Is there one kind of ice cream that is always the most delicious? And I hope from looking at this you can say, well, no, because it depends on the topping that's on that ice cream, right? If you have chocolate ice cream with sprinkles, well, that's really delicious. Chocolate ice cream with cheddar cheese, that's just weird, right? So there's a dependency between these two factors that's present in this scenario, right? And same thing for apple pie ice cream, right? Well, it can be more delicious than chocolate ice cream, right? If you are considering situations with cheddar cheese, right? But otherwise, it's less delicious than chocolate ice cream, just in general. So what this helps to highlight is that in this scenario that I've outlined here, there's actually an interaction between this first factor, the ice cream flavor, and the second factor, the topping, right? And that's really what a two-way analysis of variance is set up to help determine. Is there something about the two factors that you're investigating where there's an interaction between them that makes it so that you can't say, well, chocolate ice cream is always the most delicious, right? Or, apple pie ice cream, always the least delicious. No, it depends on the combination of these two things. So that's the whole reason to get into carrying out a two-way ANOVA. Well, it's important to realize that the analysis of variance, or two-way analysis of variance, is really a hierarchical statistic. So what it will do is, at first, the main thing to pay attention to is whether or not there is an interaction that's present, much as I've highlighted with this example with ice cream flavors and ice cream toppings, right? So that's one potential outcome from a two-way ANOVA, right? So just to re-illustrate this, if we've got flavors here on the x-axis, chocolate, apple pie, and then deliciousness on the y-axis, this is a scenario where chocolate with sprinkles is most delicious, chocolate with cheddar cheese is the least delicious, apple with sprinkles is somewhere in the middle, apple with cheddar cheese is somewhere higher, right? So if we're looking at comparing sprinkles, right, they're here. We're looking at comparing cheddar cheese, right, that is here, right? So that's an interaction effect. Now, if you're conducting an analysis, this now means, well, there might not be an interaction between factors in every single scenario. So after evaluating whether or not there is some kind of interaction present, the next step is then to see, well, if there's no interaction occurring between these factors, is there an effect of each of the factors individually? And these are referred to as main effects within the two-way analysis of variance. So for evaluating a main effect, essentially at this stage, we're looking to see, is chocolate more delicious than apple? Are sprinkles more delicious than cheddar cheese? So that might be a scenario that looks something closer to this, right? So maybe chocolate ice cream is always more delicious, regardless of the topping, right? So here's chocolate, here's apple, right? And apple, even when you add cheddar cheese, right, it's not nearly as delicious, right? So here's an effect of ice cream flavor. And maybe also, if sprinkles is always better than cheddar cheese, right? Something like this, right? This is a situation where both flavor and topping are significant, but there's no interaction between them, okay? So with two-way ANOVA, again, you're going to first evaluate, is the interaction between the factors significant, right? Because if it is, right, we can't say a simple story about what's going on with flavor or topping. But if the interaction is not significant, then we should go and evaluate, is each of these things on its own a determinant of how delicious the ice cream is, right? And then there could be another situation, of course, where past this point, maybe nothing is really significant in this scenario, right? So there's our flavor, and maybe we have COVID-19, our taste buds aren't really registering anything, it all tastes exactly the same to us. So this would be a situation where, right, there's really no significant difference. Oops. No significant difference present. So that's the overall principle, right? If you find a significant interaction effect, or if you identify significant main effects, in some situations, it then will become appropriate to go on and do a post hoc comparison. In this case, actually, if you just find significant main effects, you don't really necessarily need to go much further, because you can then just identify chocolate's better than apple pie, cheddar cheese is better than, sprinkles are better than cheddar cheese, something of that nature. But then in other cases, you may wind up wanting to go on to do some kind of post hoc analysis. So if you find a significant interaction effect or significant main effects, then you may want to go on to do a Tukey, honestly significant difference post hoc analysis as well. All right, so it's one thing for me to sort of show you the theory. It's another thing to actually put this into practice in R. So now I'm going to switch windows to RStudio, and I'm going to walk you through a couple of examples, just using a couple of the data sets that are available within R. The first one that we're going to look at involves some studies of tooth growth in guinea pigs. So to access this, I'm going to just type in data tooth growth. Okay. And then I'm going to send this to the console by holding down Command Return on my computer. All right, so now you'll see the tooth growth data set has loaded. We can look at it using the view function. I like to use this function known as str function. So if I do str of tooth growth, send that to the console, what you'll notice down here is that that's going to give us some information about what's in tooth growth. So it's a data frame, and it's got 3 different columns in it: len, sup, and dose. And what this is guinea pigs were given one of 3 different doses of vitamin C, and they were given that dose of vitamin C in one of 2 supplement types, either a vitamin, chewable vitamin, or orange juice, right? And then the growth of their teeth was measured at the end of the experiment. So, it's an interesting question to ask. Well, did the dose and or the administration method impact what was observed for guinea pig tooth growth? So one of the things we're going to have to do with this data set, right now dose is coming in as a numeric object, and we actually need to convert this to a factor. So what I'm going to do is I'm going to go tooth growth, $dose. I'm going to turn this into a factor by using the factor function, tooth growth, $dose. Okay. Run that. I'm going to go back up to line 2 and rerun the str function, and now I can see that indeed dose is being registered as a factor. Before actually doing analysis of variance, it makes a lot of sense to first plot your data. So I'm going to use the box plot function, and I'm going to put my response variable len. I'm going to use this squiggly symbol. Note that R doesn't really care how many spaces you put into your functions, so mostly that's just a matter of readability. So, and then I'm going to put len squiggly sup asterisk dose, comma, data equals tooth growth. Note that also R is forgiving. It lets you do several things in more than one fashion, so there are other ways to accomplish the same end goal. I'm going to send that down to the console, and now in my plot window, and it's a little squished here, but we could zoom in if we wanted, right? We can see now I've got these different combinations of orange juice and vitamin C, right, at different doses. So just from using our eyeballs here and evaluating this plot, right, notice at the lower dose we don't see nearly as much tooth growth. At higher doses we see more tooth growth. And something interesting is happening here where at lower doses it looks like guinea pigs that get orange juice are experiencing more tooth growth than those that get vitamin C supplements. But by the time we get up to the highest doses, there's really no difference between them. So just based on that initial observation, now we're ready to go ahead and calculate our two-way ANOVA. So to set this up, what I'm going to do is I'm going to say tooth lm, use the lm function, and I'm going to feed in the same argument that I just used in this box plot function. And to save some typing, I'll just copy and paste, right? And then I know my formula is correct because it worked when I made my plot. I'm going to run that. Then I need to run the ANOVA function on this. So I'm going to go tooth AOV of tooth lm, right? So I'm created this object tooth lm. Now I'm going to just feed that into this AOV function, right? And this is just for the sake of clarity in your code. Okay, and then to take a look at the output from this, I'm going to use the summary function, tooth of AOV, right? And down here in my console window, right, I've got output from that analysis. So notice in this output, right, I've got 3 rows. I've got a row for sup, I've got a row for dose, and then I've got sup : dose. So it's this third row, right, that is evaluating for the presence of an interaction effect. And in this particular data set, there is in fact an interaction effect, right? So, the dosage and the form both interact to determine how much tooth growth is observed in the guinea pigs, right? So at this stage, I'm going to make a mental note that overall there's a significant interaction effect. And so the next step I'd want to conduct with this data set would be to carry out a post hoc analysis. I'm just going to use Tukey HSD on tooth AOV, right? And then this is going to have kind of a horrifying list of comparisons, right, across every single possible combination of dosage and supplement type, right? You can do a couple of things here that can really help. Start at the highest or the lowest, right, and label that A, and then work your way through systematically to compare across other groups from highest down to lowest. So for example, right, in this plot, the vitamin C at 2 was the highest, right? It looks like OJ at 2 is second highest. So if we come back over here and read our way through this massive table and look for vitamin C2, let's see, here's vitamin C2, it's scattered all over. Vitamin C2 versus OJ2 down here. Okay, they are not significantly different, so those would get the same letter, right? Then, you know, let's work our way down. Vitamin C2 against OJ1, you know, not significantly different, so OJ1 here would get the same letter. OJ2 versus OJ1, statistically similar, so all 4 of these would get A's, right? So it looks like most of the interesting stuff that's happening in this data set, right, is at the lower dosages, right? So that's how to kind of go through if you have a significant interaction term. Okay, let's take a look at one other example where the interaction effect is not significant. So for this, we're going to work with a different data set, which is all about penguins. So to get this to work, we have to install a package that contains this data set. So I'm just going to run, and remember, you only have to install packages once. This data set is called Palmer Penguins. So it is some information about penguin species at the Palmer Research Station in Antarctica that's been provided from an ecological research station that's present there. Okay, so after we've installed the package, we need to load it. Okay, Palmer Penguins. Okay, and then we can load this data set. All right, so now let's take a look at this penguin data set. Same process, str function. All right, this is a data set that has a lot of different things going on. So we've got several different penguin species. There's 3 different species evaluated. They've actually been characterized across 3 different island locations. We've got a whole bunch of information about various penguin dimensions, how long their bills are, how deep they are, how long their flippers are, etc., whether they're male or female, and what year the data were collected. So in this case, we're just going to evaluate a fairly simple question, one about size differences across species and between the 2 sexes. So I'm just going to add a comment to my code to remind me of what I'm doing. Do penguin bill lengths differ between sexes and across species? And is there a significant species by sex interaction? So something going on, e.g. with variation in sexual dimorphism across species, right? So it might be that one penguin species has a lot of sexual dimorphism, another species does not have as much sexual dimorphism. That could give rise to a sex by species interaction, right? So we're going to do the same thing that we did for the guinea pig tooth data, right? And we're going to start out by plotting this. I'm just going to use the box plot function again, right? And we're interested in bill length in millimeters as related to species and sex in the penguin's data. Okay, so let's see. All right, so again, if we zoom in on this plot, right here are our 3 penguin species, and we have to, fuss around a little bit with our x-axis labels to see everything, but we've got our 3 species, all the females, and our across our 3 species, the males, right? If you play around with the order of these variables, that might be a little more straightforward to evaluate, right? But we can see there's some differences in variation in bill length across the categories that we're evaluating. So I'm just going to shortcut now to carrying out another one of those 2 ANOVAs. So we'll say bill LM, and again, you can just use good old copy and paste. Then bill AOV. Okay, then summary. And let's take a look here. So in this case, there actually is not a sex by species interaction. So I'm just going to note the sex by species interaction is not statistically significantly different. And instead in this case, we do have a species difference and we also have a sex difference. Okay, so long story short, there are a couple of different ways that we could dive in to kind of evaluate what's going on at the species level, what's going on at the level of sex. For our purposes, we're going to shortcut through this for the time being, and we can just again conduct a Tukey post hoc analysis. Okay, and then use this to go through and evaluate, where do we see similarities, where do we see differences, right? And in this case, actually, almost everything's statistically significantly different from each other, aside from the female gentoo and chinstrap penguins are similar in size to each other, and then the gentoo and chinstrap male penguins are, well, they're still below 0.05. So the only similarity we see here is actually between female gentoo and chinstrap penguins. If you look across this and evaluate it more closely, right, and it may make sense. Okay, so it may make sense to actually plot this again, reversing sex and species. Okay, so now we have males and females of each species grouped. One thing that this simplifies is we can see that across all three species, the females are consistently smaller than the males, right? And then along with that, we can also see that the Adelie penguins are smaller than chinstrap and gentoo penguins, right? So that helps us understand what's going on with our main effects in this instance, right? And it could very well be the case when you run this analysis that only one of these two things is significant, right? But you want to go through a similar process then of kind of evaluating where those differences are. So examining the plot, female penguins are smaller than males. In addition, the Adelie penguins are smaller than the other two species. Right, so this approximates what I'd wind up wanting to write about in my results section to characterize the outcome from this analysis. Along with that, you would definitely want to include an ANOVA table, right, that reports the information that's found here. Okay, I'm going to append this with one more thing. Let's go back now with our tooth data. Okay, right, to see where there's a significant interaction. So if I wanted to write about this in a results section, I would note this as there is a significant dose by supplement type interaction affecting guinea pig tooth length. So in parentheses, dose by supplement F equals 4.11, degrees of freedom are 254, my P is 0.022. Okay, so that's how I'd characterize that specifically. And then from here, I'd want to get into, what's going on across this. So at the highest dose, both supplement types produced the longest teeth, right? And refer to whatever figure this is. Meanwhile, at lower doses, the orange juice produced more tooth growth compared to the supplement. Right. And, as you're developing your results, you probably would want to get more specific about this. So figure XX, mean growth and then you want to specify what your mean growth is. Here at a dose of 1, mean of whatever that mean is, plus or minus the standard deviation. A dose of 0.5, mean of whatever that is, plus or minus the standard deviation. Okay. So that would help to build out what's going on here. One other thing that can wind up being very useful at this stage is a strategy to summarize means without having to go in and pull out every single possible combination of categories, right? Because there's 6 different categories here. So I also want to show you a function that's really helpful for organizing your data before calculating means or standard deviations. And that's actually one that's on the board behind me, right there. It's the Tapley function. So the way this works is to apply, so let's say, for example, I want to look at average tooth length based on the dosage. What I could do is say Tapley of tooth growth, $, and for the first argument here, I'm just going to say dose, right? And then I want to know something about, oh, sorry, not dose, len for length. Let's check that. Yep, okay. So I'm going to put the measurement I'm interested in as the first argument, tooth growth, $, dose, as the second argument. So I want to look at length as organized according to dose, and I want to calculate a mean, right? So as here. So if I run that line, right, that's going to give me the mean tooth growth at 0.5, 1, and 2, right? So in this particular scenario, if I want to look at all of the means for, orange juice versus the supplement, I would need to do another step to pull those apart to kind of, and then I could run the Tapley function on those individually to get those individual means, if that makes sense. Okay, well, two-way ANOVA is complicated, but I hope that this video has showed you that it's not impossible. If you are still getting stuck at some step in the process, my best advice would be to get help. But I hope that this gives you enough tools that you can go through and conduct this type of comparison and successfully report your results.